Hello everyone and welcome to iExamB, where we help you to prepare 50% faster. This is mock test 5 of our IBPS SO IT Preliminary Exam series. Over the next few minutes, we'll be going through 25 carefully designed questions spanning across computer networks, data structures and algorithms, DBMS, operating systems, programming in C and Python, OOPS concepts, software engineering, and Linux commands. This set is quite numerical and trace heavy, with several formula-based and code tracing questions. So keep a notebook and a rough sheet ready. Every time a question comes up, pause the video, work it out yourself first, and then come back to check your approach. That's how you'll actually build exam day speed and accuracy. So all the best and let's begin. This is the first question. In the RIP distance vector routing protocol, a destination is marked as unreachable when the hop count reaches which value? Now, the RIP, which is the routing information protocol, is a protocol that allows a maximum usable hop count of 15. That's the largest hop count that still represents a genuinely reachable destination. The moment the hop count reaches 16, RIP treats that as infinity. It's a way of signaling that the destination is unreachable. This fairly low ceiling is also exactly why RIP is only suitable for small networks. Anything requiring more than 15 hops simply can't be represented. And it's part of how RIP tries to mitigate, though not fully solve, the classic count to infinity problem. So here in this question, the correct answer is option C, which is 16. So here is the next question. A 10 Mbps Ethernet LAN has a maximum cable length of 2500 meters and the signal propagation speed is 2 into 10 raised to power 8 meter per second. What is the minimum frame size required for reliable collision detection CSMA CD? Now for this question, the correct answer is D, which is 250 bits. For CSMS-CD, the transmission time of a frame must be at least equal to twice the propagation delay. So the sender can detect a collision before finishing transmission. Propagation delay would be calculated as 2500 divided by 2 into 10 raised to power 8, which gives us 12.5 microseconds. Round trip time would be twice of 12.5 microseconds, which is 25 microseconds. Minimum frame size would be equal to bandwidth into time. The given bandwidth here is 10 Mbps, which is equal to 10 into 10 raised to power 6 bps, and this would be multiplied by 25 into 10 raised to power minus 6 seconds. So the answer here would be 250 bits. Now in this question, a TCP connection has a bandwidth of 1 Gbps and a round trip time or RTT of 20 milliseconds. What is the bandwidth delay product BDP representing the amount of data that can be in transit at any time? Here the correct answer is A, which is 2.5 MB. The BDP is calculated as bandwidth into RTT. So here it would be 1 into 10 raised to power 9 bits per second multiplied by 0.02 seconds, which comes out to be 2 into 10 raised to power 7 bits or equal to 2.5 MB. This represents the ideal TCP window size needed to keep the pipe full. Now come to question 4. A network administrator subnets the IP block 192.168.10.0/26. How many usable host addresses are available in this subnet? A /26 mask leaves 32 minus 26 or 6 host bits. That gives us 2 to the power of 6, which is 64 total addresses in this subnet. But 2 of those are always reserved, one for network address and one for broadcast address. So we subtract 2, leaving 62 usable host addresses. Hence here the correct answer is option B, which is 62. In this question, without memoization, how many total recursive calls does a name recursive Fibonacci function make to compute fib of 5, including the initial call itself? Remember that fib of n is equal to fib of n minus 1 plus fib of n minus 2, base cases being fib of 0 is equal to 0 and fib of 1 being equal to 1. Let's define T of n as the total number of calls made to compute fib of n, including the call itself. That satisfies the recurrence T of n equals T of n minus 1 plus T of n minus 2 plus 1. For the recursive call to fib n minus 1, the call to fib n minus 2, and the current call itself. With base cases T of 0 and T of 1 both equal to 1, now let's build this up. T of 2 is 1 plus 1 plus 1, which is 3. T of 3 is 3 plus 1 plus 1, which is 5. T of 4 is 5 plus 3 plus 1, which is 9. And T of 5 is 9 plus 5 plus 1, which is 15. So computing fib of 5 makes a total of 15 recursive calls. Hence here the answer is option A, which is 15. Now let us look at this question. Consider relation R ABCD with functional dependencies AB to C and CD to E, where A and B is the only candidate key. What is the highest normal form satisfied by R? The candidate key here is the composite key AB. Let's check for partial dependencies first. C depends on the full key AB, not just part of it, and D depends on C, which in turn traces back to the full key AB. So neither C nor D is partially dependent on just A or just B alone. That means there is no partial dependency, so 2NF is satisfied. But now look at one level deeper. C determines D, and C itself is not a superkey. It's just a regular attribute. That's a transitive dependency of the non-prime attribute D on the non-prime attribute C. And that's precisely what 3NF forbids. So this relation satisfies 2NF but fails 3NF, which makes 2NF the highest normal form it satisfies. Hence, the answer to this question is option A, which is 2NF. Now for the table employees with employee ID department salary that contains Department A salaries as 40,000, 60,000 and 70,000, Department B salaries as 55,000, 65,000 and Department C salaries as 30,000, 20,000, 25,000 and 10,000. What is the output of select department count asterisk as CNT from employees grouped by department having count asterisk greater than 2 and average salary greater than 50,000. So let's check each department against both having conditions. Department A has a count of 3 and its average salary is 40,000 plus 60,000 plus 70,000 divided by 3, which is about 56,667. That satisfies both count greater than 2 and average greater than 50,000. Department B has only 2 employees, so it fails the count condition immediately and drops out. Department C has a count of 4, which passes the count check, but its average salary is 30,000 plus 20,000 plus 25,000 plus 10,000 divided by 4, which is 21,250, well below 50,000. So it fails the average condition. Only Department A satisfies both conditions with a count of 3. Hence, for this question, the correct answer is option C, that is Department A and count 3. Next we have which of the following SQL queries correctly retrieves employees who earn more than the average salary of their own department, not the company-wide average. So the phrase their own department tells us we need a correlated subquery, one that recalculates for each outer row individually rather than computing a single fixed value once. Option C does exactly that. By adding where department equals E1 dot department inside the subquery, the average salary gets recalculated fresh for each employee's specific department, and then that employee's salary is compared against their own department's average. Option A compares against the company-wide average instead, ignoring department entirely. Option D is actually invalid SQL since having without a group by can't reference a non-aggregated column like salary that way. So the correct query for this question is option C, which is select asterisk from employee E1 where salary is greater than, and then the subquery which is select average salary from EMP where department is equal to E1.dpt. Now in this question, a B plus tree index has a fan out of 100, which means each internal node can reference up to 100 children, and each leaf node stores up to 100 records. To index 10 lakh records with maximum fan out utilized at every level, how many levels including the leaf level are required at minimum? So the answer here is option E, which is 3. Let's build this from the bottom up. At the leaf level, we need 10 lakh records divided by 100 records per leaf, which gives us 10,000 leaf nodes. One level above that, we need enough internal nodes to point to all 10,000 leaves. And with a fan out of 100, that's 10,000 divided by 100, giving us 100 internal nodes. One more level up, we need a single root node to point to those 100 internal nodes, since 100 divided by 100 is exactly 1. So the full structure is root pointing to 100 internal nodes pointing to 10,000 leaf nodes. That's 3 levels total, including the leaf level. Hence the answer here is option E, which is 3. Now in this question, table orders with order ID and customer ID has rows O1C1, O2C1, O3C2, O4C3. Table customers with customer ID and name has rows C1 Alice, C2 Bob, C4 Dave. How many rows are returned by select asterisk from orders left join customers on orders.customer ID equal to customers.customer ID. A left join always preserves every single row from the left-hand table, orders in this case, regardless of whether a match exists on the right table or not. Orders has exactly 4 rows, so the result must also have exactly 4 rows. Let us match them up. O1 and O2 both have customer ID C1, which matches Alice. O3 has customer ID C2 matching Bob. O4 has customer ID C3, but there is no C3 in the customers table at all. So that row still appears just with null in place of the name. Note that C4 Dave doesn't factor in at all here, since nothing in orders references C4 and this is a left join, not a right or full join. Hence, the total rows returned here is 4. So the correct answer here is B, which is option 4. Now, in this question, in a system using Banker's algorithm with 5 processes, P0 to P4 and 3 resource types ABC, the current state is given by the available vector, allocation vectors, and maximum vectors. Which of the following is a valid safe sequence? So at first, let's compute the need matrix, which is maximum minus allocation for every process. So P0 needs 743, P1 needs 122, P2 needs 600, P3 needs 011, and P4 needs 431. Now let's simulate starting with available at 332. P1's need 122 fits within 332. So P1 can run. It finishes and releases its allocation, bringing available up to 532. Next, P3's need, which is 011, fits within 532. So P3 runs and releases, bringing available to 743. Then P4's need, which is 431, fits within 743. So P4 runs and releases, bringing available to 745. Now P0's need, which is 743, fits within 745. So P0 runs and releases, bringing available to 755. Finally, P2's need, which is 600, easily fits within 755. So P2 completes last. Every process gets to run in this order without ever exceeding what's available. So P1, P3, P4, P0 and P2 is a valid safe sequence. Hence here the answer is option D. Now in this question, 4 processes arrive as follows. P1 arrival time is 0 and burst time is 8. P2 arrival time is 1 and burst time is 4. P3 arrival time is 2 and burst time is 9. And P4 arrival time is 3 and burst time is 5. Using preemptive shortest remaining time first scheduling, what is the average waiting time? So let us try to solve this problem. First of all, we'll build the Gantt chart step by step. Since SRTF preempts the moment a shorter job arrives. P1 starts at time 0 with burst 8. At time 1, P2 arrives with burst 4, which is shorter than P1's 7 remaining. So P2 preempts and runs from 1 to 5, completing fully. So its completion time is 5. At time 5, we compare what's left. P1 has 7 remaining, P3 has 9 remaining, and P4, which arrived at time 3, has 5 remaining. So P4 is the shortest. It runs from 5 to 10, completing at time 10. At time 10, P1 has 7 remaining versus P3's 9. P1 runs next from 10 to 17, completing at 17. Finally, P3 runs from 17 to 26, completing at 26. Now compute the turnaround time, which is completion minus arrival for each process. P1 is 17, P2 is 4, P3 is 24 and P4 is 7. Waiting time is turnaround minus burst time. So for P1 it is 17 minus 8, which is 9. For P2 it is 4 minus 4, which is 0. For P3 it is 24 minus 9, which is 15. And for P4 it is 7 minus 5, which is 2. Adding up these, we have 9 plus 0 plus 15 plus 2, which equals 26. Divided by 4 processes gives an average waiting time of 6.5 milliseconds. Hence, the answer here is option A. A system with 32-bit virtual address space uses single-level paging with a page size of 4 KB. If each page table entry requires 4 bytes, what is the total size of the page table for one process? So here, what we would do is first calculate the number of pages, which is 2 to the power of 32 divided by 2 to the power of 12, which is equal to 2 to the power of 20 entries. Page table size will be equal to 2 to the power of 20 entries multiplied by 4 bytes per entry, which gives us 2 to the power of 22 bytes, which is equal to 4096 KB or 4 MB. Hence, the answer here is option A. Now in this question, in a system where each resource type has exactly one instance, process P1 holds R1 and requests R2. P2 holds R2 and requests R3. P3 holds R3 and requests R1. What can be concluded from the resource allocation graph? Let's trace the resource allocation graph as a chain. P1 is waiting for R2, which P2 holds. P2 is waiting for R3, which P3 holds. And P3 is waiting for R1, which P1 holds. Following that chain, P1 to R2 to P2, P2 to R3 to P3, P3 to R1 back to P1, we arrive right back where we started. That closed loop is a cycle in the resource allocation graph. And critically, since every resource type here has exactly one instance, a cycle in a single instance resource allocation graph is both necessary and sufficient to confirm a deadlock. There is no ambiguity about it, the way there can be with multi-instance resources. So in this case, we have the correct answer as option C, which means deadlock exists. Now in this question, the keys 50, 30, 70, 20, 40, 60, 80, 10 and 25 are inserted in this order into an initially empty binary search tree. What is the height of the resulting tree at root being at height 0? Let's insert these one at a time following the standard BST rule of smaller goes left, larger goes right. 50 becomes the root, 30 goes left of 50 and 70 goes right of 50. Next 20 goes left of 30 and 40 goes right of 30. Then 60 goes left of 70 and 80 goes right of 70. Now 10 comes in, it's less than 50, less than 30, less than 20, so it becomes the left child of 20. And 25 comes in, which is less than 50, less than 30, but greater than 20, so it becomes the right child of 20. Now let's find the deepest path. 50 to 30 to 20 to 10, or equally 50 to 30 to 20 to 25, either way. That's 3 edges from the root to the deepest leaf. So here the height of this tree is 3. Hence, the answer is option B, which is 3. Now, in this question, using the hash function hk is equal to k mod 10 and linear probing for collision resolution, the keys 23, 45, 12, 34 and 25 are inserted in this order into a hash table of size 10, at which index is the key 25 finally stored. Let's compute each hash in order. H of 23 is 23 mod 10, which is 3. So 23 goes into slot 3. H of 45 is 5. So 45 goes to slot 5. H of 12 is 2. So 12 goes into slot 2. H of 34 is 4. So 34 goes to slot 4. Now H of 25 is also 5. But slot 5 is already occupied by 45. With linear probing, we simply move forward to the next slot, slot 6, which is empty. So 25 is stored there. Hence, the correct answer here is option D, which is index 6. According to Cayley's formula, how many distinct labeled spanning trees exist for a complete graph K5 with 5 vertices? Now, Cayley's formula states that the number of labeled spanning trees of the complete graph Kn is n to the power n minus 2. For n is equal to 5, this is 5 to the power 5 minus 2, which is 5 to the power 3, which is equal to 125. Hence, the answer here is option E, which is 125. Now in this question, you have to predict the output of the following C code. You have an integer array of 5 elements storing 10, 20, 30, 40 and 50. You have an integer pointer which is reference to the array. And you have the pointer incremented by 2. You have to print the two values, which is value of p and value of p minus 1 plus value of p plus 1. The correct answer here is A, which is 30, 60. Now the array comprises of 10, 20, 30, 40 and 50. P starts at array 0. After P is equal to P plus 2, P points to array of 2, which is equal to 30. So value at P will be equal to 30. Value at P minus 1 will be equal to array of 1, which is equal to 20, and value of P plus 1 will be array of 3, which is equal to 40. So their sum will be equal to 60. Hence, the final output would be 30, 60, which is option A. Now, in this question, you are asked what is printed by the following Python code. You have a function add underscore item with two parameters, that's item and an empty list lst. What you're doing inside the function is lst.append the item and then return the list. You are then printing add item 1, printing add item 2, printing add item 3 with an empty list, and then printing add item 4. So what would be the output? So here the correct answer is option C. Now let us go through the entire code. Python evaluates default argument values only once at function definition time. The default list is shared across all calls that don't pass an explicit list. Call 1 will go ahead and return a list with value 1. Call 2 will append 2 to that list and return 1 and 2. Call 3, which has an explicit new empty list, will return only 3 as a list. And call 4, which has a default listing still, which is holding 1, 2 from before, will append 1, 2 and 4. Hence, the final answer is option C. Now in this question, you have to predict what would be the output of the following C++ program. Just go through the program. It's an inheritance-based program where you have a class base and a derived class, and then in the main function, you're creating a derived object and also a base reference which is equal to D. And then it is calling the display function with bref as the argument. Then you have a base pointer bptr and it is initialized to the new base constructor. bptr show and then you have delete bptr. You have to predict what would be the output. Now here, because show is declared virtual in base, any call to it through a reference or pointer gets resolved dynamically at runtime based on the object's actual type. That's runtime polymorphism. Bref is a base reference, but it's bound to an actual derived object D. So when display calls b.show, the virtual dispatch mechanism looks at the real object underneath and calls derived version printing derived. Then separately, bptr is a pointer to a genuine, freshly created base object, not a derived one. So bptr show calls base's own version, printing base. Putting the two outputs together in order, we get derived base, which is option E. Now in this question, you have to predict the output of the following C code. You have three integer variables where A is initialized to 5 and B is initialized to 3. C is calculated as A ampersand B pipe A cap B. You have to print the value of C. So you have to predict what would be the output. So here in binary, A is 5, which is 101, and B is 3, which is 011. Let's compute each piece. A and B is 101 and 011, which is 001 or decimal 1. A XOR B is 101 XOR 011, which is 110 or decimal 6. Now precedence matters here. In C, the bitwise AND operator binds tighter than bitwise OR. So this expression is really A and B or A XOR B, which is 1 or 6. In binary, that's 001 or 110, which gives us 111 or the decimal 7. Hence, the answer here is option B, which is 7. Next, you have what is printed by the following Python code. A string is initialized to IBPS SO exam. You have to print S of 2:8:2 plus S of :-1 and 0:3. So let's index the string first. IBPS SO exam sits at position 0 through 9. The slice S2:8:2 starts at index 2, stops before index 8 and steps by 2. So it picks up indices 2, 4 and 6, which are P, S and E, giving us PSE. Now for the second part, S reversed, which is S within bracket :-1 flips the whole string to max, EO, SS, PBI. Taking the first three characters of that reverse string, indices 0 to 2 gives us max. Concatenating the two pieces, PSE plus max gives us PSE max. Hence, here the answer is option B, which is PSE max. So in this question, using the basic COCOMO model for an organic mode project with estimated size 50 KLOC, where effort is equal to A multiplied by KLOC to the power B, with A is equal to 2.4 and B as 1.05, what is the estimated effort in persons month approximately? Here, the correct answer is option A, which is approximately equal to 146 person months. Now, effort is given as 2.4 multiplied by 50 to the power 1.05. Log of 50 is approximately equal to 3.912. So, if we multiply 3.912 by 1.05, we get 4.108. E to the power 4.108 is equal to 60.8. Effort will be equal to 2.4 multiplied by 60.8, which is equal to 145.9, which is approximately equal to 146 person months. A software project has rapidly evolving requirements and requires frequent customer feedback with working software delivered every 2 to 4 weeks. Which SDLC model is most suitable? Every detail in this question points towards Agile. Rapidly evolving requirements, frequent customer feedback, and working software delivered every 2 to 4 weeks. That delivery cadence is literally describing a Scrum sprint. Agile and Scrum are built specifically around short iterative cycles with continuous stakeholder involvement, which makes them ideal when requirements are expected to change along the way. It's worth distinguishing this from the spiral model, which is also iterative, but its primary focus is risk analysis on large high-risk projects, not rapid customer-driven feedback cycles. Waterfall and V model, meanwhile, are rigid and sequential, requiring requirements to be logged in early, completely unsuited to this scenario. So here the answer is option C, which is Agile Scrum model. In this question, you are asked which Linux command correctly counts the number of lines containing the word error in a file named app.log. Here, the correct answer is option C, which is grep-c error app.log. This command does exactly what's being asked. The -c flags tells grep to output a count of matching lines directly rather than the lines themselves. Let's quickly rule out the others. Find with -name searches for file names matching a pattern, not text inside a file's content. So that's not even operating on the right thing. wc-l app.log or grep error first counts the total number of lines in the file, producing a single number, and then searches that single line of output for the word error, which will essentially never match anything meaningful. grep-v inverts the match, counting lines that do not contain error, which is the opposite of what we want, and head-c truncates output by byte count, which has nothing to do with counting matches at all. So the correct command here is option C. So that brings us to the end of mock test 5 of our IBPS SO IT preliminary examination series. If you'd like to track your score, note down how many you got right across these 25 questions and identify which topics need another revision. Revise well and prepare well before you appear for your IBPS SO examinations. We wish you all the best. Thank you for watching.